All right, calculus. This is a continuation of section 5.4. This section introduced the fundamental theorem of calculus, and the lessons so far have been on that topic. But for the next few lessons, for next few videos, what I want to do is address a few other sort of smaller topics in this section that come up. So the first thing has to do with absolute value, and then we're going to move towards net change. Let's say you have a function like this. This is, the function f of x here. And there's a portion of it which is above the x-axis. Let's say this is 5 units of area above the x-axis here. And let's say this unit here, this area down beneath the x-axis, this is like -2. Okay, so let's just say that those are our areas. If you want to integrate this function from 0 to b right here, you're going to include the 5 and the -2, right? So this is going to be equal to a total net area of 3. But suppose that you wanted to integrate not the function itself, but the absolute value of that function, again from 0 to b. I've just got 0 and b here. So what you do if you take the absolute value of this function is this portion of the function would stay the same. But then here, instead of having a negative part, what you'd get is you would get a reflection. You'd get a positive part. So now instead of a -2, you'd have a +2 area there. And what we'd get from this integral, I just realized I forgot the dx on the end of these things. There we go. What you'd get from this integral is 5 plus 2, and you'd get 7. Okay, so this is what happens when you take an absolute value of a function. You would have to find any part of that function that's within the interval in question. In this case, I'm going 0 to b. This could have been an a to b or whatever, you have to find some part of that function, any part of that function where it's negative. You'd have to find that, and then you'd have to swap the sign. So instead of subtracting, instead of having a negative value that you're adding on, you'd swap it and make a positive value. So that in general can be a little bit tricky because you've got to find where the x-intercepts are, right? You've got to find like the zeros so that you can determine where it drops beneath the x-axis and do a sign chart and then split up your integral into separate integrals. I'll go over an example of how to do that with this velocity function. So first of all, let's talk about what this idea of absolute value is going to mean in a real-world context. If you have a function v of t equals velocity, so here's an example function, 3t squared minus 11t plus 6. And let's say we're talking about meters per second here, okay? So if you take the integral of a velocity function, what we learned earlier in the section is that gives us displacement. So displacement, let's calculate the displacement on the interval from 0 seconds to 3 seconds. That's going to equal the integral from 0 to 3 of our velocity function, v of t dt. Let's just do that integral real quick. We're going to take 3t squared minus 11t plus 6, and we're going to find an antiderivative, t cubed minus 11 halves t squared plus 6t. There's our antiderivative. And then we'll evaluate that at 0 and 3 and get our answer here, which is going to be -4.5. So that means we have a negative displacement. That means overall our ending position after 3 seconds is behind our starting position. So if we start here, imagine a line. If we start here, if that's up, if that's forwards and this is backwards, we end 4.5 meters behind where we started. Let's draw a little graph. I'm going to draw a graph of position. And let's just do this assuming that initial position is 0. So that would mean that this is my position function right here. Okay, the graph would look something like this. If we take this t cubed minus 11 halves t squared plus 6t and graph that in Desmos, it'll give us something that goes like that. Where this is right here is 3 seconds, then we have 2 seconds is approximately here, and 1 second is there. So 1, 2, 3. And starting position at 0, ending position here is down here at -4.5. So this distance here between the starting position and the ending position is what we call our displacement. However, that's not the same as the total distance traveled by the object, right? It's the distance between its starting position and its ending position, but the total distance traveled by the object is going to be more like it went up by a certain amount and then it went down by a certain amount. And the total distance traveled would take this distance plus that distance, right? So to calculate the total distance traveled by the object being described by this velocity function, what we'd need to do is use the absolute value of the function. So total distance traveled is actually equal to, let's say on the interval 0 to 3, okay? It's actually equal to the integral from 0 to 3 of the absolute value of the velocity function, v of t, dt. That way, we'll take, instead of adding and then subtracting and ending up with a net change of negative 4.5 meters, I forgot to put a unit on this, that's meters. Instead of having the net change giving us displacement, this would take the forwards motion and add that to the backwards distance. However far this object travels backwards, we take the absolute value and add those together. So in the next video, I'll go ahead and take this function and we'll integrate the absolute value of it. And to do that, we'll have to find zeros and split it up into separate pieces. We'll go over that in a moment.